In business analytics, we like talking about probabilities. What's the probability of a stockout under a particular inventory control policy? If we're an Uber driver, what's the probability that the next requested pickup is going to come from Market Square in the middle of Knoxville, Tennessee? If we're in advertising, what's the probability that a surfer is going to click on an ad if it's placed on the top left of the page versus the top right of the page? And you know me, I love gambling, I love Las Vegas. What if I have some sort of betting system in mind, and I would like to know what's the probability that that betting system allows me to double my money before going broke? So maybe I set up a Monte Carlo simulation that plays a sequence of games and repeat this, say 1,000 different times, and my betting system results in me doubling my money 512 out of those 1,000 times. What's the probability in general that this betting system is going to allow me to double my money before I go broke? So the frequentist definition of probability helps us out. We know that we define the probability of some event occurring as the long-run fraction of trials, all of which are conducted under identical conditions, they're all independent of one another, the long-run fraction of trials where we observe our event happening. So after my Monte Carlo simulation, I doubled my money 512 out of those 1,000 times. My estimated probability would be 51.2%. Now, one drawback of the frequentist definition is that we never actually directly observe the probability of our event happening. We can only estimate it. So, for example, let's imagine I sat down and repeatedly just flipped a fair coin and kept track of the fraction of flips that came up heads. Well, the frequentist definition lets me know that the probability of heads in the long run is 50%, because if I did this an infinite number of times, that fraction would eventually converge to 0.5. And actually, if we run the simulation and just look at the trajectory of coin flips that have come up heads so far, that fraction, what we see is that that fraction looks like we've, pretty much nailed down the probability after maybe 100,000 or so different trials. But if we zoom in ever so slowly, we find that there's always some sort of deviation between the fraction of trials where we've seen our event occur and that true probability of the event occurring. That fraction is pretty close to 50%, and it gets really darn close as we increase the number of trials a lot. But it's not like we ever land at 50% with our fraction, and it stays there forever. So that begs the question, just how wrong is our estimated probability? With the doubling my money example, I've estimated the probability with my betting system to be 51.2% that I'm going to be able to do this. But how far off is that from the true probability of me being able to double my money using this betting system? And so that's what this unit is going to try to answer. It's going to try to establish what we've referred to as the standard error of our estimated probability, a good guess for how far off our estimate might be from the true probability of that event occurring. And spoiler alert, there's actually a really simple formula that we can use. We can just throw in a few numbers to it that gives us a pretty good idea of how far off our estimated probability is likely to be from the true probability of that event occurring. But I think it's worth the time to sit down and run a series of investigations, ask just the right set of questions so that we can discover this formula for our own. We'll develop a bit of insight for what this standard error looks like, how it depends on the probability we're trying to estimate and the number of trials in our experiment. And so let's try this out. First, a little bit of notation, just a quick review. N, we're going to let denote the number of trials in our overall experiment, maybe 1,000, maybe 10,000. And we'll let P be the true probability of that event occurring, what we'd like to know. We can never directly observe it, but we can estimate it with some data. And we're going to let P hat, P with that little caret over it, denote our best guess of the probability after N trials, the fraction of those trials where we saw our event of interest occur. And then finally, we're going to denote this standard error by SE. So the standard error is going to be the typical difference we expect between P hat and P, our estimated probability and the true probability of that event occurring. It's a good guess for how wrong our guess really is. So let's go ahead and investigate. Let's actually go through a case where we know what the true probability of the event we're trying to estimate is. Let's go ahead and ask a few intro stat students to help us out with an experiment where we're trying to estimate the probability that a fair coin comes up heads. We know the probability is 50%. So specifically, what we're going to ask these introstat students to do is to keep track of the fraction of flips that have come up heads as they increase the number of flips in their experiment out through, let's say, 800 total coin flips. So if we have each of those students plot the trajectory of the fraction of flips that have come up heads so far, here's what stands out. So one thing we see is that the p hat, the estimated probability, can start out really quite far away from 50%, but those p hats seem to edge closer and closer to 50% as the number of flips increases. But at any given number of flips, sometimes the estimates, the p hats, are, pretty far away from 50%. Sometimes they're relatively close to 50%. There's definitely a lot of variation that we see in these trajectories, these estimates from one student to another. So is there some sort of pattern that we can capitalize on? Is there some sort of behavior with the standard error, the typical difference between these p hats and p, with the number of flips that we can discover? So let's extend this investigation and actually have 2,000 introstat students all do this. Let's have them plot the trajectories of the fraction of coin flips that have come up heads over the course of 800 total coin flips. And so as we plot these 2,000 different trajectories, let's see how close the estimated probabilities are after any particular number of flips. And what we see once again is that the p hats can start out really quite far away from that 50% value, the true value of the probability of coming up heads, but this edges closer and closer and closer to 50% as the number of flips increases. So that decrease, that getting closer to 50% happens fairly quickly at first, but then kind of slows down as the number of flips increases. And for these trajectories, sometimes we see that some students' trajectories end up really close to 50%. Some trajectories, some estimates are, still really quite far away from 50%. So let's actually have the students do this a total of 100,000 coin flips. Let's really make them work here. And I think some clearer patterns emerge. So the typical difference between those p hats the students are measuring and the true value of p of 50% really does start out quite big, but that difference tends to get closer and closer and closer to zero. But it does so at an unequal rate. That decrease towards the 50% really happens quite quickly as we get through those first few number of flips, but that decrease kind of slows down as the number of flips increases a bit more. So let's try to do a better job at actually trying to quantify what the typical difference is between a p hat any one of these students might have measured and the true value of p with this experiment. The p hat they've measured and that 50%, the true value for the probability of coming up heads. So here's what we'll do. Let's go ahead and slice all of these trajectories after a certain number of coin flips. Let's do 100, and let's look at the difference between the value of p hat the students have recorded, the fraction of flips that came up heads, and 50%, the true value of p in this case. Well, when we make a histogram of these possible differences between p hat and p that these students have measured, what we find is a very familiar shape for statisticians. In fact, we call this shape the bell curve, or the normal curve, or the Gaussian curve. And we see this shape again and again in all aspects of probability and statistics. And it turns out that really, no matter where we slice it, no matter how many trials we decide to look at this distribution, 100, 500, 1,000, etc., we see this shape emerge again and again. So no matter how many trials we're talking about, if we look to see at the distribution of the possible p hats, how far away they are from the true value of p, that distribution looks to be well described by one of these bell-shaped curves. So the nice thing is that the bell-shaped curve has a very special property here. Let's go ahead and use this special property to define a typical difference between a p hat we might measure and the true value of p. So let's agree to do the following. Let's use the distance between the peak of this bell curve and its inflection point, the point on the curve where the curve goes from really sloping downward ever more quickly to sloping outward. So if we use this as our measure of the standard error, the typical difference between the p hat we might measure in an experiment and the true value of p, we'll find that most of the time we're going to measure a p hat that's within one standard error of the true value of p. What do I mean by most of the time? Well, let's go and ask these intro stat students the values of the p-hats they've observed. Let's go ahead and look to see, well, what fraction of those p-hats that the students recorded are actually within 1 standard error, that distance between the peak of that bell curve and the inflection point. And what we find is that about 2/3, about 68% or so of those p-hats are within 1 standard error of the true value of p, 50% in this case. And so that's what we mean by, most of the p-hats that we'll record are going to be within 1 standard error of the true value of p. So as we were slicing this, what we were finding is that the typical difference between the p-hats we might measure and the true value of p was getting smaller and smaller and smaller as the number of flips was increasing. Our estimate of p is getting better and better the more data we throw into it. So how does the size of this standard error, the difference between, or the distance between the peak of that bell curve and its inflection point, change with the number of trials? It gets smaller as the number of trials increases, but not really quite in a linear fashion. There's some sort of curvature. That standard error seems to be getting smaller fairly quickly as we get the first few trials under our belt, but that standard error starts decreasing a little bit slower and slower and slower as time goes on. So if we look at some specific numbers, what it looks like is that the size of the standard error here looks like it decreases by a factor of 2 when the number of flips increases by a factor of 4. In other words, the standard error halves when the number of flips, the sample size in this case, quadruples. And so this suggests a very special mathematical equation that might describe the size of the standard error as we increase the number of flips, the sample size n. In fact, if we go and look to see what the size of that standard error was as we increase the number of flips and superimpose a square root curve, we find that we get a very, very close agreement. So what we can say is that the standard error goes as 1 over the square root of the number of trials. As you increase the number of trials in your experiment, that standard error gets closer and closer to 0. The typical difference between the p-hat you might observe and the true value of p is getting smaller and smaller. But there's some diminishing returns. It takes a quadruple of the sample size for that standard error to decrease by a factor of 2. So that's a pretty important discovery. More data definitely buys you a bit more precision, but it's subject to diminishing returns. You've got to be quadrupling your sample size to decrease your error by a factor of 2. That's somewhat depressing, I think. Now, the flip side of this is, how does the size of the standard error change with the actual value of p that we're trying to estimate? So, if we were to say, okay, the standard error is 0.05, but our p-hat is, say, 0.01, then all of a sudden, p-hats being within 1 standard error of p doesn't really make all that much sense. It kind of breaks down. It kind of implies there would be negative probabilities. So clearly the size of the standard error actually is going to be tied into the value of p that we're trying to estimate. And so let's try to nail down what that relationship looks like. Let's go ahead and fix the number of flips that each of these intro stat students are conducting. And let's look to see, well, what does the size of the standard error look like as we vary now the probability of the event whose probability they're trying to estimate. Let's vary that from a p of 1% all the way up to 99%. And we see some patterns. When p is very small, close to 0, or when p is relatively large, close to 1, the size of that standard error is relatively small. Remember, we're fixing the sample size as we're varying p to be a particular number, like 1,000 here. When p is around 50%, when we're trying to estimate a value of p that's around 50%, well, that standard error seems to be pretty big. So what we see is kind of a fun, happy, semicircular relationship between the size of the standard error, how precise our estimated value of p is, with the value of p itself that we're trying to estimate. So, can we guess what the mathematical equation is for this curve? Well, this gives us a good chance to dust off our skills from BAS 320, the regression class, because we know how to fit curves to data. So what if we go ahead and try to predict the size of the standard error from the true value of p we're trying to estimate, and let's throw in as another predictor the square of the true value of p here. Let's predict SE from p and p squared. That gives us a nice curve. Well, if we do that, we actually get a pretty good fit. If we look at the r squared is nearly as high as it can go. 1 is the highest it can go. We're getting about 96%. Can we do any better than this? Well, let's, on a whim, instead of having our model predict the size of the standard error, let's have our model predict the square of the size of the standard error instead. In regression, we're allowed to do this. We get to choose what our model is trying to predict, if it's the original data we recorded or some transformation of that. So what if we try to predict the square of the standard error with p and with p squared as predictors? Well, if we do this, we see that the r squared of that model increases by quite a bit, up to close to 99%. And that's a really quite darn good fit. If we superimpose that over the data that we've collected, we see that, yeah, we have a pretty good match. And not only that, there's something really special that we see if we look at the coefficients of this fit. If we look at the coefficient of the p term in this fit, it's right at about 0.00124. If we look at the coefficient of p squared in this fit, well, it's the exact same number, just a negative. And so that indicates that the coefficients of p and p squared in this model are actually the same number, just with opposite signs. And it just so happens with this investigation, this was made with 800 flips here, a sample size of n of 800. It's awfully suspicious that this 0.001239 is very, very close to actually just 1 over 800. And so maybe let's kind of put this all together and propose that perhaps the relationship we're trying to discover is that the square of the standard error is equal to p over n minus p squared over n. That kind of reflects what we saw in that regression model. And it turns out that we've discovered the truth. Mathematically, you can show that this is how the behavior of the standard error works with the sample size and the true value of p that you're trying to estimate. And so just with a little bit of math, a little bit of grouping of terms, we come up with our master formula that tells us how far off our estimated value of p, our p hat, is likely to be from the true value of p that we're trying to estimate. The standard error of our estimated p is the square root of p times 1 minus p over n. So throw in the sample size, throw in the true value of p that we're trying to estimate, and that'll let us know typically how far off the p hats that we might observe after we've collected some data are going to be from p itself. Now, this formula does leave us a bit yearning because, it involves the true value of p, but that's exactly what we're trying to estimate. So we can't really use it immediately, but there's a quick workaround. Instead of plugging in p, which is what we're trying to guess, we just plug in p hat to this equation, and that's what we're going to have be as the standard error of our p hat, the standard error of our estimated probability. So how do we put this all together? We can get the numbers out fairly easily. How do we add value to these numbers? How do we interpret them so everyone can understand our results? So going back to the betting system example, where we found that p hat was equal to 512 out of 1,000. We ran a Monte Carlo simulation 1,000 times. We doubled our money in 512 of them. Our estimated probability of doubling money under this betting strategy is 51.2%. We know that estimate's wrong. It's off from the true probability. And the standard error was 0.016, or 1.6 percentage points. So how do we want to interpret this? Well, my favorite way is to say that our estimated probability is p hat, give or take a standard error or so. Or putting into the context of this problem, our estimated probability of doubling our money is 51.2%, give or take about 1.6 percentage points or so. I think that provides a nice tidy way of interpreting the value of p hat and the standard error so that we all kind of get and understand what those numbers mean. When is it okay to use this formula? Well, there are some restrictions on the number of trials, the amount of data that we've collected. This formula works pretty good, gives a pretty accurate estimate of how far off our guess might be, as long as the number of successes and the number of failures, n times p hat and n times 1 minus p hat, are both about 10 or so. So there we have it. We're preoccupied with probabilities in business analytics. We can use data to estimate probabilities, but we know that our estimates are wrong. They're going to be off from the true value of p. And this formula for the standard error, the square root of p hat times 1 minus p hat over n, gives us some pretty good insight about how far off p might be from our estimated value. So The next step is, okay, armed with a good guess of how wrong we are, can we come up with a range of plausible values for p based on our Monte Carlo simulation or based on the data that we've collected?